One of the things you'll see solder paste, you'll see, like, for example, this is a type 3 solder paste. And what type 3 is talking about there is that the actual particle size, the balls that driven out of that sieve are between the largest ball will not go through a grid of 325 openings per inch. Yeah, still by inch. And the smallest particles will not go through a 500 openings per square inch mesh. And so we have negative 325, positive 500. That's a type 3 paste, and that's going to define a given size ball. If you have a type 4 paste, which a lot of people are using nowadays because we've gone down to find a picture, I'll show you how that corresponds. That means the largest ball cannot go through a 400 opening per square inch mesh, and the smallest ball can't go through a 500. So now we're talking about basically a mixture, modulation of smaller balls. Okay, well, why? Well, we have a rule called the 5-ball rule. And the idea here is that again, depending on the pitch of the components you're doing, therefore, the size of the deposit you want to put down, that the rule is that 5 balls of your smallest particle has to fit across the width of the aperture. Otherwise, you're going to run into problems. So let me give you an example. Okay, here we have, let's say we're using a type 3 paste, and we're doing, look at, third one down. So our largest particle, I think I said smallest particle, let's go, it's the largest particle, let's go across the aperture. So our largest particle in a type 3 paste is approximately 1.77 mil. And let's say we're putting a 20 mil pitch part. That means when we reduce our aperture, that we're actually, the aperture itself is going to be 10 mils wide. If we divide 1.77, that largest particle, into 10 mils, we come out with 5.6. Hey, we made it. 5.5 balls basically could fit in there. That's cool. I know you don't see half balls, but we know we've got the right space. Now let's say we're using that same type 3 paste and we have a 16 mil pitch part on our board. Well, again, that largest particle that we have to fit 5 across is 1.77 mil. But now we only have an aperture that for a 16 mil pitch part, that's approximately 8 mils across. It doesn't quite fit, only 4.5, which means, yeah, it might work, but a lot of times it might not, in which case we're going to get inadequate volume. And it's going to affect how it's going to release and everything else, and also, how it's going to print. So if we move down to a type 4 paste, where our largest particle is 1.5, and for that 16 mil pitch, we have an 8 mil wide aperture, we can fit 5.3. Hey, we're okay, we're over 5 balls wide. So that's the rule, and this rule has been around for a long time, and it still holds up really, really well. The other rules that we have are what we call the, we have the area ratio rule, and this is the one that we stick by. And again, this all goes into stencil design, which you guys probably be involved in. But the idea here is that we're looking at the holding force of the solder paste, the pad. And so we talk about transfer efficiency, that the holding force of the paste, the pad, has to be greater than the holding force of the paste, the stencil aperture. Otherwise, it's not going to release. So what we do is we calculate the area of the opening of the aperture, and we divide that by the area of the aperture walls. And if it's greater than 0.66, we meet the standard for the area ratio. So here's what that looks like. We got the area of the opening, length times width, and then we're dividing that by the area of the walls, the thickness, and there's where your thickness of the stencil comes in, versus, of course, the area with length and width. And so we do that, we calculate that out, and as long as we're greater than 0.66, we're going to get good transfer efficiency. And this is what it looks like for a round aperture, for those of us who like round apertures. And of course, it's just basic geometry. And the thing about it, so you can see that the thicker the stencil we go, the more most likely we're going to meet that area ratio. Whereas we go too thin a stencil, we may violate it. And so we violate it, we get what we call too tall and thin an aperture. In other words, we're not meeting that ratio because our thickness isn't enough, assuming we've done the geometry in length and width, or in this case diameter. And what happens is it just doesn't release it properly. So here's an example. Oops, hey, come back here. Okay.